Hello, everybody, and welcome to week 3 of Earth 10 Antarctica. And we now move from talking about climate to a more geology-centric unit. If you've taken Earth 2 or if you've taken another geology class at UCSB, some of this material might be familiar. If you haven't, it may come across that I'm skimming over some basic concepts, and that is to bring us back to Antarctica as soon as possible. And that is unfortunately a bit of a necessity for a class that covers this much material. I'm happy to elaborate more upon some of these concepts if you want to ask me outside of class. In this half of the lecture, we'll learn about plate tectonics and go over the theory. And in the second half of the lecture, we'll talk more about the different types of boundaries between tectonic plates and what examples of those different types of plate boundaries exist in Antarctica. Now, a reminder that the second lab, which is the Ocean Currents lab, is due this Friday, April 16th, and I recommend reading the materials put together by the TAs and attending their sessions for help, especially because there is a lot of material in the climate lectures, and the presentation that TAs put together does a nice job of summarizing it and summarizing what's going to be most useful for the lab. And also, the first lecture quiz is up. Lecture quiz number 1 will close on Sunday, April 18th, and it actually does not include this lecture that I'm about to give, nor will it include lecture 6. It covers the material from the first 2 weeks, not counting lecture 1, which is just introductory material. And there is a review session that I hosted earlier today, but the April 12th review session, which is now uploaded and recorded, covers the material that will be on the quiz. So that is uploaded, and the slides for it are also uploaded on GauchoSpace. So today's topics flow right from one to the other, and I'll briefly outline the different physical layers of Earth to set us up for the concept that Earth is made of different plates that move, at least at its surface. We'll talk about how, before that was understood, scientists used bits of evidence to come up with the theory that Earth's continents have not always been where they are today. And that's something I've alluded to in past lectures in the context of Antarctica and its past geographic location over geologic time. And the second half of lecture will delve into the forces that drive plate tectonics as best as we understand them. And then we spend a while on the different types of plate boundaries, and I go over some examples of how those different types of plate boundaries exist in Antarctica. So to begin with, we know today that the Earth is composed of different layers, and one somewhat confusing aspect of that is that the layers are defined a bit differently depending on whether you want to talk chemistry, for example, how much silica versus iron different layers have, or if you want to talk physics, which is whether a layer is a solid or a liquid, and if it's a solid, how it behaves. Now, a key thing to consider for this class is that physically, solids behave differently under stress. A rock or a brick, if you put it under the stress of pulling it hard enough or smashing it, will bend until it can't bend anymore, and then it will break. But some solids don't do this. They change shape without breaking, and they instead deform. And these are known as plastic solids, with some good examples being silly putty and butter, at least at certain temperatures. Now, I bring that up because the warmer a solid is, the more it can deform. And even rocks, if they are warm enough but not quite warm enough to melt and be a liquid, can actually deform plastically. So physically, the two uppermost layers of the Earth are in fact two solid layers that behave in different ways. We have the lithosphere, named lithos because it means rock, and that is the rigid uppermost physical layer of Earth. It lies over the asthenosphere, which comes from the word or the Greek root asthenos, without strength, and it's named because it's ductile, weak, and flows under stress instead of breaking, but it is in fact technically a solid. There are other physical layers of Earth, but we won't delve that deep for this class. The important thing to remember is that the lithosphere floats on top of the flowing asthenosphere, and that is the basic mechanism that allows plate tectonics to happen. So these uppermost layers are where you're going to want to focus. And one thing to consider is that chemically, the crust and the mantle are defined differently than what you saw on that diagram. The lithosphere is kind of like pond scum floating on top of the asthenosphere, and the lithosphere consists of the crust and the uppermost part of the mantle. chemically, the crust is the outermost layer of the Earth, and it's defined by having the most silica, chemically, of any of the layers. It lies over the mantle, which has a bit more iron and magnesium and a bit less silica. The lithosphere is made of the crust and the very uppermost part of the mantle, because there is a different physical definition from the chemical definition. The crust is very, very thin, and it is what we are walking on. It is also what underlies the ocean floor. And there are actually two slightly different types of crust, one that forms under oceans and one that forms on land. The surprising thing to you might be that we have these two different types of crust, and one of them occurs under the ocean. So you would think that it would form as it does because the ocean is there. It turns out that the oceanic crust actually usually forms on land to begin with, and because it sinks so low down, the ocean will flood to cover it. So the ocean ends up where the oceanic crust is, actually, not the other way around. And the crust is joined to the uppermost portion of the mantle to form the lithosphere. The bottom of the lithosphere, the asthenosphere, and the lower mantle, which doesn't really directly get involved in plate tectonics as much, all have more or less the same chemical composition, but they physically behave very differently, and so we have to be careful with that definition. And the tectonic plates that give the name to plate tectonics actually consist of pieces of lithosphere, the crust and the uppermost part of mantle being dragged along over the weak, flowing, ductile asthenosphere. And if we turn to Antarctica, Antarctica lies on one of these lithospheric plates, one known as the Antarctic plate, which has remained relatively stable and mostly the same size throughout geologic history, but it's not always been in the same place. It's not always actually been so close to the South Pole. Antarctica is what's known as a craton, which is a large mass of continent that has been stable for billions of years. And there is also a craton underlying South America, which lies nearby. And you can actually see where the plate boundaries are marked on this diagram. These blue dots represent earthquakes, and the red lines represent volcanoes. And not every single volcano is on a plate boundary. You'll notice that there's a bunch in Antarctica, which we'll talk more about later, but you find a lot of volcanoes along plate boundaries. You can see there's a kind of a little plate here known as the Scotia plate, and between the South American and Antarctic plates, you have a couple of little microplates, and their motion is mostly controlled by the larger plates. You'll see in Lab 3 that they mostly exist to accommodate movement by the larger plates, excuse me. And so the Scotia plate and the Sandwich plate are two of these microplates found in the subantarctic islands region. And they'll come up again because they feature a subduction zone, a particular type of convergent plate boundary. That's one of the type of plate boundaries we'll talk about. And plate tectonics is the unifying theory of geology, just as the theory of evolution is to the biological sciences. And it is a rather young theory, actually. It has only been established for less than a century. My grandmother turned 80 this year, and she went to college when plate tectonics was being taught as a hypothesis, but had not been accepted as the unifying theory of science, or of geologic science, excuse me. And that's remarkable to me because it gives us a sense that these scientific discoveries weren't actually that long ago. They were within, in some cases, the lifetimes of our parents and grandparents. And it also seems a little bit simplistic, and the simplisticness, it seeming simplistic hides the fact that there is a lot about the mechanism that drives it that we still don't understand, because simply we can't go into the mantle. But what it postulates is that the lithosphere is not a single mass. It is broken into interlocking moving plates that flow over the asthenosphere, and this process drives mountain building, it drives earthquakes, it drives volcanic eruptions, and it indirectly or directly drives most geologic processes. And one thing we'll talk about is that when people began mapping the locations of earthquakes and volcanoes out, the locations coincided with plate boundaries. And they also coincided with the presence of mountains to begin with, or the presence of a Midocean Ridge, which is an underwater mountain chain. And so the Antarctic plate, the plate that Antarctica lies over, is thus one of several large plates, along with a lot of smaller plates that jostle around and move extremely slowly over the Earth's surface. And this is key to understanding why Antarctica's current climate exists and why it hasn't always been that way. We now know a good amount about the Earth, how it is physically and chemically layered, but that is a recent development. First, people had to come up with the idea that Earth's surface might even move at all before they considered what might be driving it. And Alfred Wegener, who was an Austrian scientist, was not the only person to come up with the idea, but he was the first to compile enough evidence to publish in a scientific journal, and he cited several other people who had made observations that turned out to be important. And that's how all science works. Even if the work is attributed to one person, they are going to be building on someone else's work to some extent, and there are going to be collaborators. He was a physicist, and his work was essentially him thinking something is wrong with this picture and coming up with 4 bits of evidence to suggest that Earth had moved around, that the continents have not always been where they are now. And he used that evidence to come up with a hypothesis that Earth was not static and that it seemed like the continents had moved. He died before he ever found a mechanism, but his observations, along with others, would be revisited when more advanced scientific techniques allowed a mechanism to be discovered. And so I have the 4 bits of evidence on here. The first was that he observed that fossils of either the same or very similar organisms were found on widely separated continents, and these were organisms that were not marine animals. And fossil hunting was starting to really take off, even though people didn't necessarily understand exactly what these fossils were or how they were related to one another. But people could at least observe, okay, these 2 skulls look like the same animal, or these plants are the same. And not only were they finding these strange animals and plants and other organisms, but they were discovering that these species were in widely separate locations. For example, there have been a lot of fossils, including Mesosaurus, which is this. It's a swimming reptile, but a reptile that swam in rivers and lakes and wasn't suited to swim over the open ocean. And it's been found in the Congo and Angola, as well as in Brazil. And what I'll actually get to are the same rock formation. And the other big example outside of the animals on either side of the Atlantic Ocean are finding these animals in both Africa and Antarctica, or both Africa and Australia, or India and the other southern continents. And one thing I'll get to is that India, until very recently, was a part of a continent that consisted of most of the southern continents, and it's only recently been attached to the rest of Asia. And so they found fossil ferns on widely separated continents. They found amphibians and this mammal ancestor, Lystrosaurus, which was actually the first fossil ever described from Antarctica. It's been found in Antarctica, as well as southern Africa, and India as well. And this animal could swim, but it isn't clear. It would not have been able to swim across an ocean. It was basically a hippopotamus. And there was no way that these 2 fossils could have gotten there unless some divine force put them there, which some people speculate that kind of thing, or that the continents had been connected at one point. And it also provided evidence that places like Antarctica that are cold today might not always have been, because they found Glossopteris, a plant that was literally a tree. We do not have trees in Antarctica today. It doesn't support that, but clearly it once did, since fossils have been found. And this is the diagram that you'll see in one of the upcoming labs, a fossils lab later on. And this shows something we know today, that the southern continents were at one point attached into a single supercontinent. You have the same animals found on either side of what is now the Atlantic Ocean, which means the Atlantic Ocean has not always existed in geologic time, nor has the Southern Ocean. At one point, Antarctica was actually attached to all the continents that are now on the opposite side of the Southern Ocean. And it's interesting to think about the fact that Antarctica has a close geologic history with these other continents, where in some cases, with some of the more recent species, they've found fossils of plants in Antarctica that are very closely related to plants that are still alive today in Australia, New Zealand, and New Caledonia. They've survived in those places because it's not a frozen wasteland. In Antarctica, as we'll talk about, very little life has survived, but not none. Now, another thing that alerted Wegener and others to the possibility of continental drift was The fact that some of the continents look like they should fit together if you put the coastlines together, and they look too similar and fit too well together if you sort of treat the continents like a jigsaw puzzle, for this to be a coincidence. The most obvious example is the coastline between Eastern South America and West Africa. And this is something that I really get a kick out of still, because I noticed this as a kid. And it's an observation that, at least once maps were made well enough for people to do this, it is sort of something that a kid could spot. And actually, it's true. It's really good to think about how a lot of science people act like it's this grand scope project, but a lot of it is just simply doing something with your observations and making the right observations. And one thing you can see in this diagram actually is this is a Google Earth image of the Atlantic Ocean, and you can see some texture in the middle of the ocean if you look closely. And that, in fact, is the very feature that has pushed Africa and South America apart and made ocean underneath. But the key thing is that Wegener did not know that existed. He could see how the shapes fit together, but he couldn't see what was going on under the ocean, and that contributed to him being unable to find a mechanism. They also found glaciers in the tropics, glaciers that I apologize if that got cut off. I'll make sure to fix that. But glaciers were found they found evidence of glaciers that had clearly been at sea level, that weren't mountain glaciers. And something we'll talk more about during the glaciers unit is that glaciers leave a very telltale record behind. They leave surfaces that look polished. They leave glacial flour with occasional large drop stones. So you'll find really fine-grained sediments in the rock record. You'll also find something like this, where you have layers of ocean mud that have been turned to rock, and then there's just this boulder in the middle of the nice layers. And that's from when glaciers reach sea level, as they do in Antarctica, and large rocks that have been plucked by the glacier get carried out to sea and then dropped as the glaciers start to melt out in the ocean. So they found these drop stones in places like China and Brazil and all over Africa and in India. Kind of the reverse situation of finding ferns in Antarctica. They found that some places now that have very hot or more temperate climates clearly had glaciers on them, which for one thing indicated that Earth's climate had changed quite a bit over time, but it also suggested that maybe a place that is pretty close to the equator now, like Brazil, might have been closer to the North or South Pole very far back in geologic time. And this is something scientists came across more as they explored the rock record. This is something that scientists began to discover as geology developed as a science, as people began to learn how to look at rocks and determine what sort of processes had made those rocks, looking back in time. And the last thing is that sort of summarizes, it actually summarizes some of the other ones quite well, and it relates to rock types. It relates to, for example, finding not only the same fossils on two separate continents, but the rock that those fossils are found in turns out to be just about the same rock. It shows the same textures, the same mineral composition, and the same features, along with the fossils, too many similarities for it to just be a coincidence. And scientists would also observe mountains with similar structures, mountains that had similar folding structures on either side of the Atlantic Ocean, or rocks from southern South America and southern Africa and India and Antarctica and southern Australia having very strong similarities. And this indicated that something had happened to separate these continents, that the same forces had been affecting these continents until something happened to separate them. And you really do want to notice how often the Atlantic Ocean and the Southern Ocean and the southern continents come up, because the Atlantic Ocean is, geologically speaking, a relatively new ocean. The continents that were on either side of it were connected not all that long ago, geologically speaking. And Antarctica being by itself has been a relatively recent phenomenon. The southern continents were, until recently, attached to Antarctica. So this does seem like good evidence to me. And perhaps it seems like good evidence to me because I now know what the mechanism is in hindsight, but in the 19th and early 20th centuries, Wegener did not have that mechanism. Wegener couldn't come up with a mechanism that drove all of this that actually made sense. he ran into the issue, for one thing, of assuming that the continents moved a lot faster than they actually do. It turns out that they cover about as much distance in a year as your fingernail would grow in that same year. He also proposed mechanisms that turned out to not be plausible. That, for example, that the Earth's rotation caused continental drift, or that the gravitational pull of the moon and other planets had a role. And those two do actually have some influence on the forces that drive plate tectonics. And for one thing, we'll talk about how a lot of it relates to movement of material in the mantle, and the moon pulling on that can cause changes, but that's not the whole story, and it's still not really that well understood how they play a role. And those weren't the mechanisms that actually explained how this had been continuously happening over long periods of geologic time. He was also a physicist and not strictly an earth scientist, and a lot of people didn't take him seriously for that reason, which indicates that it's actually often good to have people who are outside your field making observations, because it turned out that Wegener was onto something. And so the discovery much later on, after Wegener's death, that would actually provide a mechanism was the Midocean Ridge. And the Midocean Ridge is the feature I pointed out earlier as texture in the middle of the Atlantic Ocean. And the Midocean Ridge, a Midocean Ridge is it's a mountain, essentially, a low, elongate mountain that often will runs as a more or less continuous chain of narrow rift volcanoes, like fissures. And these fissures run all the way up and down the Atlantic Ocean. The interesting thing is that this is actually a volcano. This is new oceanic crust being produced at a volcano, a chain of fissures that runs all the way from Antarctica up to Iceland. And so a process that we now know as seafloor spreading is occurring all up and down the Midocean Ridge underneath the Atlantic Ocean. And there are several mid-ocean ridges. There are a number surrounding Antarctica, in fact. The one under the Atlantic is one of the longest, and nobody knew this existed until the early 20th century because nobody had seen under the ocean. But by this time, we had sonar and other technology that let people see what was under the ocean, and the world wars had also increased the presence of European and American military boats over the Atlantic. So what happened was that a geologist on board identified the existence of an underwater mountain chain, and people had not thought that there were mountains underwater. People had thought the seafloor was a flat, uninteresting surface, and it turned out, no, there's a lot going down there. In fact, there is this process of there is, in fact, plate tectonics going under there. There is this chain of volcanoes, and plates are moving to either side of it, and that actually is part of the mechanism that drives the continental drift that we were talking about earlier. And this is seafloor spreading, the process by which new oceanic crust is produced. And I mentioned that it's a chain of fissures. They're staggered a bit. They don't form a completely continuous chain. You'll notice that there are these spreading centers where lava bubbles up. And then there's this segment where you see the two conveyor belts moving in opposite directions, and that connects another fissure here. And this animation, by the way, is one of several linked in the Tanya Atwater animations link under General Course Resources. She's an emeritus professor at UCSB who developed a number of animations to show plate tectonics that I think are quite useful. So there are a few things to notice here. One is that the crust is produced on either side of the vent, and they're going out in both directions on either side of the vent. And new lava bubbles up and solidifies to form rock, and this goes on and on. And the name of the segments that connects them is a type of plate boundary. The interesting thing about mid-ocean ridges is we actually have two types of plate boundaries. We have what's known as a divergent plate boundary, where the seafloor spreading is occurring, and then the different spreading centers are connected by transform plate boundaries. These plate boundaries where the crust on either side is moving in opposite directions. Now, it's not easy to see that the plates are moving apart in real time because the movement is exceptionally slow. So the scientists had to confirm this hypothesis that the crust was heading in opposite directions away from these volcanic centers. And one method the scientists used to confirm that was magnetism. And magma actually, it has small flecks of iron in it. And when that magma or lava cools, lava if it's at the surface, the iron is going to point in a certain direction based on Earth's magnetic field. And Earth's magnetic field will flip periodically. And this actually causes the iron that is in magma to point in different directions because magma is pretty fluid. However, when the magma solidifies, the iron is kind of locked in whatever position it finished in, and so it won't be affected by subsequent changes in Earth's magnetic field because it is locked up in solid rock. The interesting thing about this is that you end up with a record of rocks that show these shifts in Earth's polarity between normal polarity and reverse polarity symmetrically on either side of the mid-ocean ridges. In these diagrams, you can see that there's magma with iron that is showing normal polarity being produced right now, and there's a little bit present on either side, and then about the same, and then on the left, there's a zone of reverse polarity, and then on the right, about as far as the left zone is from the center, there is a zone of reverse polarity. And then going to the right, you hit a zone of normal polarity, and going to the left, you also hit a zone of normal polarity. And they've color-coded these to show you how they've been able to date these different periods of normal polarity and reverse polarity and find out that, okay, these are the same dates. The rock is being produced on either side of this spreading center, and it's symmetrical. And this discovery supported the idea that seafloor spreading was occurring, that the rock that was formed at the spreading center was indeed ending up in either direction. And there's another variation of these animations that shows you this. You'll notice if you look at the spreading centers themselves, they'll be colored white to show normal polarity, and then you'll notice there's a couple of periods it shows on here where it's just a very brief shift to reverse polarity from normal. And that very brief shift is recorded on either side of the spreading center. Again, this is idealized, but this shows you that the spreading is occurring symmetrically, that the changes in the polarity of Earth's magnetic field are being expressed symmetrically on either side of these vents. And I mentioned that they were able to figure out how old the ocean floor was. And scientists in the 20th century became able to date rocks using radioactive decay, which we'll talk a little bit more about next lecture. And they found that the rocks at the center of the mid-ocean ridges, like the Mid-Atlantic Ridge or the various ones around Antarctica, were the youngest, and that as you moved away from the spreading center, they got older symmetrically. If you went, say, 5 miles to the left of the spreading center and 5 miles to the right of the spreading center, the rock on either side was the same age. And this also confirmed that most of the oceanic crust wasn't actually that old. And it made people wonder what happens to the oceanic crust. And that would lead to the discovery of subduction zones or trenches, because it turns out oceanic crust is recycled. Oceanic crust is produced at spreading centers at mid-ocean ridges, and it is recycled at trenches in subduction zones. And the subduction is what takes care of the old oceanic crust. The oldest oceanic crust that we have is about 200 million years, and oceanic crust is usually subducted before too long. It turns out one thing we'll talk about is that the continents do not subduct this way. The crust underneath the continents is much lighter and so does not subduct. So we have continental crust that is as old as that is several billions of years old. Not quite the age of the Earth because we don't have any solid rock from quite that old. And so oceanic crust will either meet continental crust or it'll meet another plate of oceanic crust, and whichever one is more dense will sink underneath it and be recycled into the mantle. And this is why the Earth doesn't simply get bigger and bigger from seafloor spreading over time. The plate re-enters the Earth at a trench, like this trench here or this trench here. You'll notice this is occurring with oceanic under continental, and this is where two oceanic plates are coming together, and the oceanic plate that is slightly denser is subducting. And a good chance is that that is actually the older plate, that the crust on this side is older, because older crust is cooler and denser. The crust gets cooler and thus denser as you move away from a spreading center. And you'll notice here that in both the continental example, there's a volcanic arc, and in the ocean example, there's an island arc forming. And it turns out subduction is a big driver of what makes volcanoes. And I mentioned before that earthquakes and volcanoes look like they coincide with plate boundaries, and indeed they do. An important bit of evidence for the theory of plate tectonics was actually extensively mapping the locations of large earthquakes and the locations of volcanoes, and people realized that earthquakes were occurring at the Midocean ridges, but you'd have small light earthquakes, and then you had a lot bigger earthquakes in places like the Himalaya, which it turns out is a plate boundary where two continental plates are colliding, or Japan, where you have an offshore trench and you have subduction, which leads to large earthquakes, or California, where you have two plates with continental crust grinding past each other, or the Andes Mountains, where you have an ocean plate subducting under this continent. And the interesting thing about volcanoes is that most volcanoes do indeed occur at plate boundaries also. And we'll talk about why you get volcanoes at different plate boundaries later. One thing that bugs me a little bit is that this map maps the largest volcanoes, and there are technically lots of little volcanoes at these divergent plate boundaries, at these spreading centers. But you get a lot of volcanoes at subduction. You get a lot of the large destructive volcanic eruptions at subduction zones, which are a type of plate boundary. But you'll notice that there are a few examples where you have volcanoes occurring really far from plate boundaries. This one in Africa is not a great example because this is believed to be a plate boundary that's just forming, but you'll notice that the Hawaiian Islands are out in the middle of the Pacific Ocean, and there is not a plate boundary in the middle of the Pacific Ocean. And you'll also notice there's some record of volcanoes a bit inland to North America, a bit away from the coast, and the Yellowstone hotspot is actually a good example of that. They're the magma responsible for the hot springs and for a chain of eruptions that extends from Washington over to Wyoming. That's caused by another hotspot. And hotspots are an example of a way that you can get volcanoes away from a plate boundary that we'll talk about. You'll also notice that you have some in Antarctica. Antarctica is actually, the coast is far from a plate boundary, but you have some hotspots making volcanoes. And the last animation I'll show here is one that gives you a nice time-lapse animation of how the Atlantic Ocean opened up. You start with two continents that are joined, and then you get a spreading center where where mantle material is upwelling and melting. And as you get more of this oceanic crust, which is denser and sinks lower physically into the lithosphere than does continental crust, you get an ocean filling in. And over time, over the course of about the last 120 million years, the Atlantic Ocean has formed and subsequently gotten wider. You can also see the Pacific Ocean is getting smaller. There's subduction happening on the west coast of South America that is causing the oceanic crust under the Pacific Ocean to subduct and disappear. So in the second half of this lecture, we'll talk more about the different types of plate boundaries and get a little bit into what that means for Antarctica's geology.